Students often ask me if there's a better way of learning polyatomic ions, one that doesn't involve so much memorization like flashcards and things like that. I think I might have a solution here. We're going to talk about something called oxidation states. I think this will give us a system of learning polyatomic ions that makes it feel like we're able to build them and understand them from scratch. I'm not going to say there's no memorization in this video, but my hope is as much as possible you'll feel how polyatomic ions work on an intuitive level. So let's get started. You're going to need a periodic table, and I'm going to nickname this the periodic table of oxidation states. Oxidation states, this is a system for keeping track of charge throughout an atom, an ion, a molecule, an ionic compound. It's a way of keeping track of charge. And we're going to think of charge for all the atoms involved in our polyatomic ions, and we're going to use that to calculate the overall final charge on that polyatomic ion. The reason why we're forced to use this term oxidation states is technically speaking, it's not an actual charge. What charge comes from is a measurement or a really good calculation. So oxidation states technically aren't charges, but they do a good job of keeping track of charge throughout molecule or polyatomic ions. So we're going to use this oxidation state system. All right, let's get started. So the most important thing to know is oxygen. Oxygen, we are always going to think of as being a -2 oxidation state or a 2- charge. Notice with oxidation states, the convention is often to put the plus or minus in the front of the number, whereas when we're talking about charge, we put it in the back. That's not going to affect the math of what we do so much, but just get used to me writing the plus or minuses in the front. I'm often not used to that, but I'll try my best to stick with that today. So oxygen, -2. The reason why oxygen gets a -2 score is because of its strong electronegativity. Oxygen, for most elements on the periodic table, when it's bonded to them, it's going to win the tug of war for electrons. And as it draws electrons closer to itself, it's going to have negative charge on it. So oxygen, we will give an oxidation state of -2. And I'll put in a little red box. The only exception for oxygen would be fluorine. Fluorine is the only element more electronegative than oxygen, and so we will give it an oxidation state of -1. In fact, when fluorine bonds with oxygen, it will win the tug of war with oxygen. Fluorine is not discussed too much typically when talking about polyatomic ions, so it's probably going to be left out for the remainder of this tutorial. All right, so oxygen -2. Oxygen -2, always, always, always. Now, let's get oxidation states for the rest of the periodic table. So group 1 will be +1. Group 2 is +2. So far, this probably feels like a charge table that you did when talking about valence electrons or ionic compounds or something. And yeah, so far it's pretty much the same. 1, 2, 3, 4. Metals lose electrons to get to a previous noble gas. And then we can talk about how nonmetals will gain electrons to get to previous noble gas. 3-, 2-, 1 - 0. All right. But we're talking about oxygen getting involved here. So check this out. This is pretty interesting. When oxygen bonds to any of these elements, what's going to happen is that oxygen will make that other nonmetal act more like a metal. That other element it's bonding to, because it's less electronegative than oxygen, oxygen will win the tug of war for electrons from it. So this nitrogen group here, group 15, the pnictogens, will be more like a +5. up to a +5. That may feel a little weird. Nitrogens with +5s on them, not the 3-. Yeah, it could happen. Up to a +5 is possible. And everything in group 16, the chalcogens, we're really talking only about sulfur on down. That's going to be +6, up to +6. And then group 17, up to +7. And then even in the noble gases, you involve oxygen and or fluorine. Most of them will stay noble, but krypton and xenon sometimes you can form compounds with oxygen and or fluorine. All right, so we kind of just go like this: 1, 2, 3, 4, 5, 6, 7, 8 on the periodic table. Those will be the charges on those atoms when involving oxygen. So we're going to use these oxidation states to figure out the charges on some common polyatomic ions. So before we continue with the oxidation state method, I will mention something. There is a little bit of some memorization perhaps. I think it is helpful to know or be very familiar with some of the polyatomic ions that end in 8. So let's talk about that briefly here. You know what? Let's just do a whole run through of 8s actually. If you know your 8s versus ites, stuff like that, you can probably skip this section, but I suspect for about half of you, you'll want to hear this. So when you have a polyatomic ion that ends in 8, you know, stuff like nitrate, sulfate, carbonate, etc., that 8 ending represents a polyatomic ion in its most common and often a most stable form. All right, so I kind of think of this 8 as my default ending. All right, so when in doubt, your polyatomic ion will probably end in 8. Okay, so important for this discussion though is that any polyatomic ion ending in 8 will typically, not typically, always have the highest number of oxygens attached. Okay, 8 means the highest number of oxygens attached. And to learn your ites, to get your polyatomic ion for when it ends in ite, you're just going to do the same as 8, but you will subtract 1 neutral oxygen atom. So I talked about nitrate earlier. Nitrate is NO3-. All right, we could do a quick Lewis structure for it. This video is not about Lewis structures, so, but I'm just putting it out there. All right, so it has a structure like that. You have 1 nitrogen atom and 3 oxygen atoms on it, and that's nitrate. Okay, and yeah, there's resonance, but we're not going to talk about resonance here. Different video. Nitrite would be NO2-. Same charge as nitrate. Same everything, same nitrogen, same oxygens, other than having just 1 less oxygen. We remove 1 neutral, maybe I should add that word, 1 neutral oxygen atom, keep the same charge, everything else the same except 1 less oxygen, and this would now be called nitrite. All right, and if you're into the Lewis structures, you would get you know, the one with 2 oxygens, so on and so forth. I don't feel like doing the whole thing, but that's not the correct Lewis structure if you're grading me. I know. But yeah, 1 less oxygen. All right, so this means something really nice. If you know the 8s, you automatically know the ites. So as I always tell people, learn the 8s first. Then you'll know the ites automatically. So let's talk about a nice little system for learning the ites. All right. I'm going to call this the 3-4-3 method. This is a new periodic table. Okay, 3-4-3 method. I'm not claiming to be like the inventor of this. A student and maybe a video or two I watched a while ago, they talked about like a T-4-3 method. So this is pretty similar to that. The T-4-3 method involves silicon, but I'm not going to involve silicon here. I'm just going to leave it out. So 3-4-3. Let's do this 3-4-3 method. So here is going to be our 3. Okay, you'll have to use your imagination a little bit. See, it kind of looks like the number 3 if I was doing like a block art or something. So that is our 3. And then we'll make another block art for 4. And there's our 4. So 3, 4. And then, oh, I put my 4 in the wrong place. Well, that's why we get a lot of periodic tables. Okay, there's our 3. And then here's our 4. Okay, as a block art. And then there is our other 3. All right, 3-4-3, the 3-4-3 method. And again, I'm not claiming to make this up. There's like a T-4-3 method out there I heard from my students and maybe saw a video or two on it a while ago. So 3-4-3 method, here's what the 3 stand for. Okay, 3 stands for 3 oxygens on 8. The polyatomic that ends in 8 will give it 3 oxygens. And the 4 stands for 4 oxygens on the 8. Okay, so 6 of them will have 3 oxygens on the polyatomic ion name that ends in 8. And then 5 of them, in the number 4, will have 4 oxygens. All right, the most common one being like a sulfate maybe. All right, so let's do this. Let's put 3 oxygens on the B3, BO3. You know what? It might be a little cleaner if I get a mu periodic on me. All right, so let's just reconstruct this. Nope. That's my 4. And then here's my 3. All right, I'm not going to edit this to perfection because this was a student request. So I'm trying to get this out as fast as possible. So, so here's where my boron was. Here's where my carbon was. And here's where my nitrogen was. I'm just filling this in. All right, great. So here's a 3. Here's a 3. And here's another 3. Here's a 3. Here's a 3. And then here's another 3. And then here's my 4 section. So I'll put 4 oxygens. 4, 4, 4, 4. All right. Now, here comes the part with charge. And the charge I'm going to cover again when I get back to the oxidation state method of teaching the polyatomic ions, but this 3-4-3 method also has a cool little trick for charges. I mean, perhaps this will be enough for you and you won't even need to learn the oxidation state method. Then great, awesome. So in the first three, you're going to go 3, 2, 1 for the minuses. So we'll go 3 minus, 2 minus, and then a 1 minus. And then for the 43 part, we're going to go 3, 2, 1 again. So we're going to go 3 minus, 2 minus, 1 minus. All right, so let's do that. 3 minus. Now let's do all of our 2 minuses. And let's do all of our single minuses. Let's finally give names for each of these polyatomic ions. Okay, this is, again, the 3-4-3 method for 8 ions. 8s. All right, so boron becomes borate. Carbon becomes carbonate. Okay, in a lot of minerals, carbonates. This is nitrate. Hopefully I gave myself enough room. Nitrogen becomes nitrate. Phosphorus becomes phosphate, like your bones and teeth. Arsen becomes arsenate. Sulfur becomes sulfate. I know some people want to say sulfurate. Selenate, selenium becomes selenate. Tellurium becomes tellurate. Chlorine, chlorate. Bromine, bromate. Iodine, iodate. All right, and just like that, you can bash out a lot of your polyatomic ions. And again, if you know the 8s, you'll automatically know the ites for the ones that have ites. Like nitrate has a nitrite, sulfate has a sulfite, chlorate, bromate, iodate have ite versions as well. Okay, but back to the oxidation states. For some people, they have trouble like memorizing these charges or feeling it on an intuitive level. So I want to speak to that. So let's start with something like borate. So borate we had in the +3 oxidation state column. Let's see if we can construct borate on an intuitive level. So borate, we are told, BO3, 3 minus. But now we're going to try to answer the question, why? So let's keep track of charges here. We're going to have a boron, or oxidation states, I should say. So we pretended boron was a +3. And I know half of you are going to write 3+ anyways, and honestly, I don't really care. So boron +3, oxygen -2, oxygen -2, and we have a third oxygen. We got Halloween coming up, so boo! Oh, I put a -3, -2. All right, so we're going to do the math. What is 3 minus 2 minus 2 minus 2? 3 minus 2 is 1, minus 2 is -1, minus another -2 is -3. So we get the -3, and look, we have, we got the charge down. All right, let's keep going. Carbonate. Carbon. Oh, so we're going to see if we actually get that 2 minus formula. So we get carbon, oxygen, oxygen, oxygen. 4 plus, -2. See, I screwed up the plus in front. I don't really care. So 4 minus 6, we get a 2 minus, and boom, there is the 2 minus. All right. Nitrate, you get the same thing. I'll do the nitrate one on video. If you want to beat me to it, pause and then we'll see if we get the same answer. All right, so nitrogen, 5 plus, O2 minus, O2 minus, O2 minus. No. We're learning polyatomic ions. No, 5 minus 6. We get a -1, right? See, we got it. We got it. All right. And then so on and so forth. You know, this works for everything. Just to get on video, let me do like maybe a sulfate last, which has 4 oxygens instead of the 3 that we were kind of getting used to here. So let's do a phosphate or sulfate, whatever. SO4 2 minus. Are we going to get this 2 minus? Sulfur. Where's sulfur at? It is in the +6 column. And we get 1, 2, 3, 4. So I'm done with my dad jokes. I'll let you come up with one. 6 minus 8, yeah, we get 2 minus, and there it is. And phosphate, it would be 5 minus 8, and you get a -3. And I'll let you do the rest of them for your own fun and learning purposes. So yeah, that is the oxidation state method of learning polyatomic ions. Once you know the ites, then you'll just know what the ite is by not doing the oxidation state method anymore. But like if I wanted to know, hey, what's a sulfite? So if this is sulfate and I want to know sulfite, I would just take the same sulfate, but I would remove an oxygen and I get SO3 2 minus. The oxidation state method, I must note, only works for the ate ions. It does not work for the ite ions. So learn the ites and then do the ites by hand that way. All right. I do get asked sometimes, well, if the oxidation state method doesn't work, then what is the real oxidation state on sulfur? That's not something I require my students to know at like a Chem 101 intro chem level, but if you're curious on a sulfite, sulfur, oxygen, 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 oxygen's always 2 minus, whereas for those other oxidation states, remember, it is up to those numbers. It doesn't have to be those numbers necessarily. So sulfate, let's see, little algebra here. We need to arrive at a 2 minus. So we ask ourselves the question, what minus 6 is equal to 2 minus? So 4 plus. 4 minus 6 is equal to 2 minus. So this would have sulfur in a 4 plus oxidation state. All right, so this isn't all the polyatomic ions though, so we can use this to understand other polyatomic ions as well though. All right, so let me go through some of those. All right, so let's walk through other polyatomic ions that exist. Let's first cover hydrogen-containing polyatomic ions. So one of the most important is hydroxide. Okay, hydroxide you can think of as 1/2 of water. So like if you have an acid source, which gives protons, and then you add it with a hydroxide source, a base, you know, acid plus base, you get H2O water. With this similar thinking, we can kind of justify how hydroxide is made. So O2 minus is called oxide. And if you add a hydrogen to it, a hydrogen cation, you get OH minus, so hydroxide. Hydroxide becomes hydroxide. Okay. Where does this hydrogen come from, you may wonder? Well, that comes from acids, but acids often feature something called the hydronium ion. H plus doesn't exist freely in water. It's usually attached to a water molecule. So you get H2O plus H plus gives you this H3O plus called hydronium. Okay, so we have hydroxide, we have hydronium. Common thing to do for cationic positive polyatomic ions is to end it in a like ammonia. Ammonia, you add a H plus to it, you get an H4 plus. Ammonia becomes ammonium. Okay. Most polyatomic ions they have you learn are negatively charged, but these are two examples that are positively charged. All right, so let's do more of the negatively charged ones. Notice for a hydrogen-containing polyatomic ion, the tendency is to put like a hydro sort of thing in front. You're going to see a similar but a little bit different thing for some of the other ones. All right, so like sulfate, SO4 2-, this is sulfate. If this reacts with an H plus, you get hydrogen sulfate. So this is called the hydrogen sulfate anion. This is also known as bisulfate. So that's why we couldn't use the bi prefix earlier. It can also mean that you added a hydrogen to a polyatomic ion. Also notice that the charge went down from a 2- to a 1- because we added a H plus to it. So once again, the theme is if you know the 8, you know the other ions as well, whether the ites or hydrogens containings. Speaking of ites, here's sulfite. And now we'll get HSO3-. This is known as hydrogen sulfite or bisulfite. And because both are acceptable, you're usually asked to know it both ways. Right? So let's put this to the test. If you had a compound like sodium with a bisulfite, we would call this sodium for that part. And then this part, you just drop the anion name, bisulfite. So polyatomic ions may be a little hard to learn, but once you have them down, then the naming is just a matter of putting the names together. So hopefully that makes it not as bad. So I wanted to close this video showing a list of polyatomic ions I like to show my students. The goal of this video wasn't to go over every single polyatomic ion that exists. There'd be too many, nor was it to go over a list of every polyatomic ion that appears in like a typical Chem 101 or Chem 111 intro or like first semester college chemistry class. I can just show you the list I like to give to my 101 or 111 students. Depending on how the flow of the semester is going, sometimes I do ask them to memorize and be familiar with all the polyatomic ions, whereas some semesters, maybe I was a little slow teaching a topic or something. What I might do instead is rather than having them memorize them, I just ask for like some familiarity. So for example, this is probably what I'm doing this semester. I'll give the list of ions, but just without the names. I feel like I've been doing that more often in recent semesters. So I'll leave everything here except without the names, but they will still see like the top ones put in bold. And so what I want students to do in this scenario is at least be familiar with the 8 versus ite system that we talked about. So in this scenario, I'd be like, okay, when you get your exam, just fill in the blanks. So a student would be like, okay, borate, carbonate, nitrate, phosphate, sulfate, so on, so forth. And then from there, they can deduce the other names like, oh, here's hydrogen phosphate because I added a hydrogen to it. And then 2 hydrogens would be dihydrogen phosphate. Oh, and this is 1 less oxygen with a hydrogen, so that's hydrogen phosphite. So I think those are deducible. Now, one thing I didn't talk about yet, oh, this is missing something. So what's going on with these halogens? They all seem to have 4 different prefixes that are possible, or names that are possible. So if you're learning the 8s, like with that 3-4-3 method we talked about earlier, the 3-4-3 method would identify chlorate, bromate, iodate. But there's actually a higher oxidation state chlorine possible, a +7, and that would lend perfectly to the oxidation state method we talked about earlier. So if you're learning like the chlorates, bromates, iodates with the oxidation state method, that would involve a chlorine +7 and then 4 of the oxygen 2 minuses, so that would be a -8. So 7 minus 8 would be a -1. But instead of being called chlorate, that'd be perchlorate. Per coming from the prefix of hyper, meaning a lot of something. But we don't say hyperchlorate, we say perchlorate. I didn't come up with the rules. Hyperchlorate sounds cooler, in my opinion. But so if you go 1 oxygen more than chlorate, it gets called perchlorate. If you go 1 oxygen less, it's chlorite. And 1 even less, you get hypochlorite. Like bleach is sodium hypochlorite. And notice how the lower oxygen amounts end in ite, whereas the higher oxygen amounts end in ate. Hypo comes from having an exceptionally low amount of something. Like hypoglycemia means low blood sugar in the biology world, right? So that's how you can make sense of these halogen containing anions. They all do the same thing, except fluorine does not have any of those. All right, and then here's kind of a list of like miscellaneous ones. I mean, we talked about some of these earlier, but like acetate's really important, but students often struggle with that one. What helps me with acetate is it follows a 2-3-2 -1 pattern. So it's like a 2-3-2 -1. It kind of follows a mountain in my head. Cyanide is a 1-. Peroxide and persulfides I only put on bonus questions because they're weird. It involves oxygens and sulfurs being 1- each instead of the usual 2-. That breaks from the normal pattern of charges and oxidation states. So I personally leave that only for bonuses. And here's some polyoxometallate polyatomic anions. Notice how they're not like fully consistent. Some start with a per, but other ones don't. And there's sometimes even like orthos involved. So yeah, I usually don't ask too many questions from these other than maybe I'll do chromate and permanganate are pretty common in many laboratories. So I'll sometimes ask about those. But if you're into the oxidation state method, permanganate involves a manganese +7 center. And going back to periodic table here, for permanganate it goes 1, 2, 3, 4, 5, 6, 7. So maybe you can justify the oxidation state that way in the manganese. And then chromium +6 is involved in the chromate and dichromate polyatomic anions. And so that works for the other metals on that list as well. But yeah, and those polyoxometallates, I will give the names for those on the exam. I don't expect them to know those. So really only those first 2 tables I'm interested in students having some familiarity with them. And again, a good semester, I do ask them to memorize. But usually I just provide a blank list. So Anyways, I think that's enough for this video. Let me know if there's anything you want me to cover further, and I'd be happy to do it. But hopefully this helps with you understanding the polyatomic ions rather than just simply memorizing them. All right, thank you and take care.